All right, so here's where we left off on yesterday with hopefully the video that you all watched or zoomed in. So here's the deal. So what we did yesterday is that we started the graphical addition of vectors. So the reason that I go through that, and just so you have like a basic idea, is that because if I don't do that step and I jump right into trig functions, it's an absolute train wreck. So this is why I said, okay, let's get an idea of how this deal is going to play out. So if you look on, and this is what I'm looking for, like for example on number 6, okay? So let's say you're going to do number 6. And so you've got, and I'm just going to sketch this out. You all will actually draw this to scale, but this is what I'm going to be looking for. So you can have vector B, okay? All right, 3 centimeters at 90 degrees. Okay, remember everything is measured around from that positive x-axis. So when I say 90 degrees, I know that's 90 degrees. Then you got vector C, which is 4 centimeters at 120. So here's what's important. This now becomes a new x and y coordinate system. So it's just like the only thing you use this point for is to draw the next vector, okay? This is just the beginnings of a new system, okay? It's like a whole new start. So from this positive x-axis, I'm going to measure around 120 degrees. So what you're actually going to do is you are actually going to take your protractor, and I find it. I've never run into this in all the years of teaching this, and I failed, and I blamed the geometry department because they're going. The kids are going. I don't know how to use a protractor. I was like, do they not make you do measurements and constructions in geometry anymore?
Well, they did, but it's been a couple of years.
Okay, they did, but just you've kind of forgotten it.
Yeah.
Okay, but you think they did make you do it?
They did, yeah.
Okay, all right, thank God. All right, so anyway, so you're going to put this up here like this. You're going to measure around 120 degrees, and you're going to go up here like this. So you come up here like this, okay? And then that's going to be whatever length that is, okay? And then that's vector C, 120 degrees. Now, and then you got D, which is 6 centimeters at 250. So again, you're going to go here, you've got 180 to here, so that leaves you another 70 degrees down here like this. So you can come down here like this, doink, okay? And then here's the whole kicker. And what we're after is that resultant. Okay? Now, what you're going to do is that you are actually going to measure that length. You're going to take your ruler and you're going to measure this length. Okay? Then, you're going to give this angle from this initial positive x-axis. Okay? So you're here, and you're going to go around here like this. So, just off this sketch, I know this angle has to be more than 180, or less than 180 degrees, but pretty close to it, okay? So what I don't want is, don't measure this angle right here, okay? This isn't the angle that you want. You want this angle coming around here like this, okay? So that angle should be around about 165 degrees-ish on number 7. Excuse me, on number 6. Should be around 165 degrees. And then oddly enough, your angle on number 7 should also be around 165 degrees. So both of those should be around there. Got that? We're good. Fantastic. Okay. Now, let's talk about number 8 with Bob. And some subtleties that play into number 8. So this is a situation where you want to choose a scale. So don't try and draw this thing, 3.8 kilometers long, which would be about 2 miles. All right, don't draw it. It's like that's a big vector to draw. this is where you choose a scale. Let a centimeter equal a kilometer. So you got this first vector, and you're going to come down here like this, and then you're going to go something out here like this. Okay. Now, and this is going to play out large when we get into forces as well. Okay. So here's what you've got. On this one, there's two situations. On the first one, you're saying how far in what direction should the search party travel to find Bob? So here's the difference. If you're the search party, you're going to be going this way, okay, to get to Bob. So if you're the search party, you're going to give that angle from that positive x-axis around like this, okay? Now, the next unit is on forces, okay? And we're going to spend a lot of time talking about forces. So every force problem that you're going to deal with can only end up in one of two ways, okay? There's only one of two options with any force problem. Either all the forces are balanced out and you're at a constant velocity. So like right now, there are forces acting on all of you. Gravity is trying to pull you down towards the center of the earth, okay? The chair is providing what we call the normal force, which is pushing you up and keeping you from falling down. So right now, if I were to add together all of the forces acting on you, the downward pull of gravity and the upward force from the chair, they would add up to equal to 0, okay? That's what would happen. Now, I won't do this because I like Party Girl, but if I went to the Party Girl and I grabbed her to hold of the chair and pulled that out from underneath her, she would begin to accelerate because then the forces wouldn't be balanced, okay? Same thing is true. If you want to jump up in the air, okay, like this, your upward force has to be greater than the gravitational force that's trying to pull you down. Because if it's not, you just do this, okay? You don't get anywhere. So anytime something accelerates, the forces do not add up equal to 0. If the forces do add up to equal to 0, you're just at a constant velocity. Now, that constant velocity might be at rest, like you all are right now, but it also might be pushing, like this remote control, across like this. So if I push this at a constant velocity like this, it's still moving at a constant velocity, and all the forces add up to equal to 0. Hold on. Okay. No worries. We're good. I have to think. Hold on. Josh is back. Okay. We lost Josh, and now we have Josh back. Okay. So, when you draw the forces in this tip-to-tail method, if you draw the forces and they don't end up back at the origin, that tells you the direction of the imbalanced force. So if I pulled the chair out from underneath Party Girl, she would have an imbalanced force pointing downwards, and that's the direction that she would accelerate, okay? If you add, so what's going to happen here, this is the situation, if these are forces, this object would be accelerating in this direction, okay? So maybe it's a block of wood, you know, you have something pushing it up this way, you have gravity pulling it down, you have another force that's pushing it down this way, and all those forces together would make it accelerate in this direction. So, here's the kicker. If you're the search party, you're going to walk in this direction, okay? You're going to come around like this, and that's going to be your magnitude. And if these were forces, you would accelerate in that direction. Now, here's the next question. If you're Bob, though, and you want to end up back at the base camp, here's the difference. You're going to start here, and it's going to go up in this direction. If that's the case, then you're going to measure this angle like this. So here's the difference. If you're this angle has to be more than 180, but less than 270. If you're this angle, it's got to be more than 0, but less than 90. Now, one of the questions I ask you, and this is one of my pet peeves, I say, what's the relationship between the direction and magnitude of the search party's path and Bob's path? Here's what I don't want you to say, okay? Don't go, well, they're different angles. Okay, dear Lord, no. Or the angle changes, all right? That is so nebulous, okay? It's so nebulous. And by the way, and I don't know, and I've noticed this in the last, I don't know, maybe 3 or 4 years, like, I'll ask you guys a question, and like you feel obligated like to restate the question when you answer it. Like you would say, oh, Bob's da-da-da-da-da or whatever, okay? I wrote the question. You don't have to restate the question, for the love of God, okay? Okay, it's annoying because then I have to waste my time reading all of that. Just answer the question, okay? Don't restate it. I know what the question is. I wrote it, okay? Oh, okay. Anyway, so don't have the word change, don't have the word different. Okay, it's too nebulous. More words in the English language than any other language to express ideas. Take advantage of that. So, here's what I want you to see. Is that if these were a set of forces, and this last force puts you back up here, the system would be in equilibrium and you wouldn't accelerate. If you draw the forces and you end up here, and there's a gap and there's a resultant, then it's going to accelerate. So literally, every force problem you are going to do is only going to end up in one of two things. You either end up back here, like Bob ends up back here, and you're at equilibrium like you all are right now, or there's a gap and you accelerate like if I pulled the chair out from underneath party group. Okay? Got the difference? We're cool. All right, so that's top trig functions. So we're going to talk about number 9. So let's just do a quick review of trig functions, because God, if y'all can't remember how to use protractor, God knows what's going to happen with your trig functions, okay? So we're only going to deal with 3. Sine, cosine, and tangent. So does anybody remember what sine is equal to? Opposite over hypotenuse. Cosine is going to be adjacent over hypotenuse. And tangent is going to be opposite over adjacent. So they still teach you Chief Sakatoa? Okay, I didn't know if that had like come out of favor. You know, it's like being in, politically incorrect. I had never heard of it until I started teaching it, and I'm going, wow, okay. I had one kid, he had absolute phenomenal sense of humor. And he was just, he was, fair-skinned, blonde-haired, and they were teaching that. He just wanted to mess with the teacher. And he goes up to the teacher and he goes, I'm of American Indian descent, and I find that to be, kind of rude that you teach it that way. And the teacher's going, oh my God, I'm so sorry. And he goes, I was just kidding. You're good. So, anyway, yeah. Okay, so here's how this is going to play out. So keep in mind, you're not going to have this on. You're going to have. Hopefully, you should know this. It's also on your equation sheet. Okay. If you don't, it's there. You don't have to memorize it. Okay. So here's how this plays out. So let's say you've got vector A, okay? And all I want to do is just kind of make a sketch of these, okay? We're not, you don't have to draw these to scale. We're just going to make a sketch. So here's the deal. So you got 5 centimeters at 0 degrees. And what I want, and again, this is just a sketch. You all don't have to do this. We're like this, okay? So here's what I want you to get out of this idea of trig functions. Is that the idea of trig functions is that it's going to allow us to get to the same endpoint using x and y coordinates as we would if we just drew the vector. So in case you haven't noticed, when you draw these vectors out, it's cool, it's kind of therapeutic. Oh, I have a protractor and ruler that I get to draw and measure, and it's kind of cool, right? But odds are there's going to be some variance in your answers, okay? If you compared all of your lengths and all of your measurements, there's probably some variance in your answers, probably maybe even 2 or 3/10 of a centimeter in your overall result, and maybe a degree or two in your angle. And it's kind of time consuming to draw these out, and you don't get to use a calculator, and it's a pain. But it's a way to understand it. So one way to get to this point, okay, out here, is to realize, wow, I can go 5 centimeters at 0 degrees. I can get to that point. The other thing that I could do is that I could sit here and go, okay, here's my origin. What's the x and y coordinates of this point? Okay? So in other words, instead of saying, hey, Rachel, I want you to go 5 centimeters at 0 degrees, is there another way that I could go to Tina and go, hey, I want you to get to the same point, but I want to use x and y coordinate systems. So the other thing that I could do, and this is, you get into like these x and y ideas. So if you look at this 5 centimeters, all of this is in the x direction, and none of it is in the y direction. Okay? So I could sit here and go, okay, I could tell Mr. Nelson to come out here and go, hey, you need to go 5 centimeters in the x direction and nothing in the y direction, and he can get to that exact same point. So all I want on here, so it's got vector A, x component, y component. All you have to do is say, okay, the x component is 5 centimeters, and the y component is going to be 0. So here's the point. If I tell Parker to go out 5 centimeters in the x direction and 0 in the y direction, that would be the exact same as telling Rachel to go 5 centimeters at 0 degrees. I'm going to end up at the exact same point. It's just 2 ways to get to the exact same point. Okay? Now, B is the same thing. B is just all in the y direction. So B has nothing going in the y direction, and all of it, nothing in the x direction, and all of it in the y. So B's x component is going to be 0, but the y component is going to be 3 centimeters. Okay? All well and good, right? That's if they're all on one axis. But where you run into trouble is when you get into like vector C. So on vector C, I've got 4 centimeters, and I'm just going to make a sketch, okay? So I got 4 centimeters at 120 degrees. So now, what I've got to find is this x and that y. So, what you could do, and it would be a little bit time consuming, but you could do it. You could measure over 120 degrees, and you could draw this line 4 centimeters long. And you could measure the length of this x, and you could measure the length of this y. So, but here's the grand scheme of things, okay? If you measure that x and y component, this is what's called deconstructing the vector, okay? Deconstructing the vector is a very, very fancy way of saying, oh, find the x and y components of it. That's all we're asking you to do, is just find the x and y components of this. So, I could either draw a line out here at 4 centimeters at 120 degrees, or I could come over here in this x direction, turn and go in the y direction, still end up at the exact same point. It's a personal preference on what I do. But the beauty of this x and y coordinate system is that we're going to end up at 90-degree angles. So remember, sine, cosine, tangent, they're wonderful, but they only work on 90-degree angles. So this is what we're trying to do. Now, pretend right now that that 120 degrees doesn't exist. And I'm just going to tell you that I have a 4 centimeter long vector at an angle of 60 degrees, and I want to find the x and y components of this thing. Okay, so forget about the 120. We're going to get back to that. You'll see why I picked 60 in just a second. So let me give you a quick lesson in history. Okay, let me show you how trig used to be done. So this is a lab manual from 1921. Okay, looks about 100 years old. And no, this was not my book when I was in school, so don't ask. I'm not that old. So, but if you look at the back, any good chemistry, physics, math book had this table. And what it was a table of sine, cosine, and tangent. So, because calculators, number one, in 1921 didn't exist, okay? And if you wanted the numeric value, you had to look this up. So, even when I was going through school, this is how I learned how to do trig functions, is that we had tables like this. So to give you some idea of how even computers have changed, in the early 1970s, out in Cheney, Kansas, if you've ever been out to Cheney, Kansas, if you like the Sedgwick County Fair, the science department there paid, I think, like $300 for a calculator. Now, in the early 1970s, you could buy a pretty decent used pickup for $100. Okay, that's a true story. You could buy a good used pickup for $100. So the science department paid $300 for a calculator that would add, subtract, multiply, and divide. That was it. They couldn't do logarithms, couldn't do natural logs, couldn't do anything. And other science departments from around the area would go to Cheney High School to see their calculator. Okay, because it was, I mean, that was cutting edge technology. I mean, you guys had a calculator. Wow. Okay? Because before, when you did math, you had to use these slide rulers. So, when they could add, subtract, multiply, and divide, that was cool. Now, you know, your phone has, you know, infinitely more mathematical capabilities than that thing did. All right? And so that kind of shows you how much technology has changed in a relatively short amount of time. So for the cost of 3 good used pickups, they had a calculator that would add, subtract, multiply, and divide. Okay? So imagine like a good used pickup now is like, I don't know, say $10,000, okay? So in an equivalent money, that would be $30,000 that our science department would pay for something that would add, subtract, multiply, and divide. They were going, that's crazy. But at the time, that was cool. They were cutting edge. So here's what you would do. Number one, this table stopped at 90 degrees. Okay? You couldn't look up 120 degrees if you tried. But I could look up 60 degrees. So I could come into like 60 degrees and find the sine or the tangent or the cosine of 60 degrees. And it was an actual number. So you'd look up the number that was associated with 60 degrees, and then you would use your slide rule and you would actually multiply that by whatever that is. Okay? So this is how trig functions used to be done. This was always kind of like the most used page when you got to that, because everybody was going and looking up these values because you didn't have a calculator that could do them. Even when I was in high school, the calculators weren't really good enough to really handle trig functions. So that's why they still taught us to use these. Obviously, you look in a book now that you don't have them because your calculators can do all the trig functions. Okay. But here's the deal. But here is the bigger truth. So this is 4 centimeters, and I want to find this y component. So I know the angle, and I'm trying to find the side opposite. So what am I going to use? Sine, cosine, tangent. I know the hypotenuse, and I want to find the side opposite. Sine, cosine, tangent. Party girl.
Sine.
Huh?
Sine.
Yeah. So the sine of theta is going to equal that side opposite divided by the hypotenuse, and the hypotenuse is going to be the vector itself. Okay? So anytime you're deconstructing a vector, and you are going to deconstruct a lot of vectors, okay? You are always going to be given the hypotenuse, and you're always going to find the x and y components of it. So in this situation, then the y component is going to be the vector times the sine of the angle. Okay, there you go. So then my x, then we're going to use cosine. So that's going to be v times the cosine of the angle. So somebody take, on this y component, somebody take 4 centimeters, and make sure you're not in radian mode. times the sine of 60 degrees, and then somebody take 4 centimeters times the cosine of 60 degrees. And I know that should be 2.00 if I remember right. So somebody take 4 times the sine of 60. What'd you get?
3.46.
Okay, 3.46 centimeters. So here's what we've got. So I'm going to draw this a little bit bigger. So my x component is 2 centimeters. My y component is 3.46 centimeters. Okay? And there was that 4 centimeters. So here's the deal. I can either go out and up, or I can just go out like this at 60 degrees. Now, here's what I wanted to do off the 60-degree angle. In my mind, because this is just how I learned to do this, even though this original vector was at 120 degrees, because this has to add up to 180. So personally, and again, this is just how I learned how to do it. I'd go off the 60-degree angle here, and then I'd use that 60-degree angle to find the x and y components of it, okay? Now, your calculators will handle 120 degrees, but this is, visually I always found that tough to think that, oh, if I take the sine of 120 degrees and multiply that by 4, in my mind, you know, the side opposite of 120 degrees should be something out here like this, okay? The side opposite shouldn't be this side over here. Now, but here's what's important, and this is where occasionally you'll find this shocking. Your calculator will lie to you, okay? And you'll see that later on. So here's the deal. When I make this sketch, what's the sign of my x component, positive or negative? Negative, so I gotta have a negative x with a. So this is a good idea why you make this sketch, because I've seen some kids' calculators, and it was just weird, I saw this yesterday. They were given like the wrong sign of this. So this is why you want to make this sketch, so that you know that you have the correct sign of your x and y components. So on here, okay, so with that vector c, 4 centimeters at 120 degrees, you should have an x component of, since it's actually here like this, okay, here's your 120 degrees, so you're going to have an x component of negative 2 centimeters and a y component of 3.46. Okay, so that's what you should have for vector c. Now, then you got vector d, and we're going to do the same thing. You don't have to make a sketch, but it's handy. So here's vector d, which is 6 centimeters at 250 degrees. So, again, if it were me, okay, if it were me, I'd come in here and I'd work, so this whole thing is 250. So that means that angle is 70 degrees. So you can either use like the sine, cosine, and go off of 70 degrees, or you can plug in the 250. It's a personal preference thing, okay? But here's the deal. You're in the third quadrant. So what sign does your x component have to have? Positive or negative? Negative. What about your y component? Negative. So you have to think this through and make sure that your calculator is giving you the correct x and y components on this thing in terms of sign. So let's make sure everybody's got this. So somebody plug in either the 70 or the 250, I don't care. Give me my x component and give me my y component. And do not be in radian mode. You're going to get really jacked up answers. So Janine, which I heard in when you were playing tennis in middle school, that you were always called Jeannie.
Yes, that is true.
Yeah.
Yes.
Yes.
I've been through a lot of names.
Okay. Okay. So what is what'd you get for your x component then? Hopefully negative something.
You could make it negative.
Okay? What your calculator says your answer is?
Negative 5.1. Nope, negative 5.2. It's probably wrong. I'm having a slow day.
Yeah, something's horribly wrong. Yes?
I got negative 2.05.
I like that. What did you get?
We'll move on.
It's all right. I'm trying to help.
Okay. Wow, okay. So,
It's okay.
okay. I'm a little bit worried, okay? We're good?
Yes. Yes.
So then, what did you get for your y component then? Negative something.
I mean, I wasn't good yet. I'm gonna be good.
You're gonna be good, because it
Yes.
is the weekend.
Yes.
Yeah, okay. So what did you get for the y component? Negative 5 point something.
2.
Huh?
2. Am I still wrong? Oh, this is awful.
What'd you get?
I got negative 5.63.
Does it round up?
Yeah, 6.4.
Okay. You have, because this assignment's going to be a train wreck if you can't figure out how to get these answers.
Yes.
Okay? I'm just telling you. I mean, if you don't have these numbers right, this is the easy step. And everything else is going to be a train wreck from there on out. So, figure out what's wrong with your calculator. Do an exorcism, do something, okay?
Okay.
And you're not in radian mode.
No. It's okay. I can ask
What are
Rachel
you
about it
plugging in for
later.
your numbers?
Huh?
Like, what are you typing in?
What did you put in?
I put in the sin 70 times 6.
Oh, I put 60. I figured it out. And then I switched them around. It's okay.
It's all good?
Uh-huh.
Okay. Because you had me worried there.
No, we are all good. I just can't subtract.
Okay. All right. It is kind of an important skill. Okay, so vector E then, because that's just 5 centimeters at 180 degrees, that's just going to be negative 5 centimeters and 0. So here's what you should have, okay? Because if these are wrong, what we're going to do next is going to be wrong. So you got A, B, C, D, E. You should go 5, 0, negative 2, negative 2.05, and negative 5, and you should go 0, 3, 3.46, negative 5.64, and 0. So this is what you should have on this bottom section for the x and y components. Okay? Cool with this? Okay. Now, we're going to do these on the back side. We're going to have vector D, B plus D. Now, I'm going to show you a couple of ways that you can approach these problems. How you do this is up to you, okay? This is what I would do, okay? I'm a very visual person. I like to have an idea of what's going to happen. So, and I'll show you both techniques. And again, you don't have to do this. It's just a suggestion, okay? But what I would do, I'd come in and say, okay, here's my x and y coordinate system. So I got vector B, which is 3 centimeters at 90 degrees. Okay, so here's my vector B. And then I've got vector D, which is going to be down here like this. Okay? So imagine this. I've got Parker, this is like a tug of war. Okay? So I got Parker pulling this way, and I got Tina pulling this way. Okay? It's like a tug of war. So, or it's like a soccer ball, and you're kicking it that way, and you're kicking it that way. So where's the ball gonna go? Something in here, right? Okay, ish, right? Because we're kicking it there, we're kicking it there, it's a tug of war, boom. It's gonna go something in here, right? Just like a ballpark idea. So if just by making the sketch, and this is what we call a free body diagram, I know this angle, wherever I end up, has to be more than 90, but it has to be less than 250 degrees. So I know if I get an angle something different than that, I've done something wrong. So if you like that idea of that free body diagram, make the sketch like that. Now, what some people like to do is they'll make the sketch of that tip to tail. They'll go, okay, here's B, and then here's D, boom, there's my result, okay? Some people like to do that. But again, here's what's important. The advantage of making the sketch is that you get an idea of what's going to take place. And you have an idea, when you get your answer, does it seem reasonable? Okay, that's all you're trying to do. So here's what we're going to do. If you look on the sheet of lecture notes that I gave you, which I don't have a copy of, but there's these steps that you need to go through. The first step is that you find the individual x and y components. So what we're going to do is we're going to draw this chart. We've got B, D, the sum, x, and y. So here's what we're going to do, is that we're going to look at the x components by themselves, okay? So we said that B's x component was 0, okay, so it has no x component because it's all in the y direction, okay? So we've got that. And D's x component was negative 2.05. So remember, sigma means sum, so we're just going to add these numbers together, and we're going to get negative 2.05. So here's what we've done. So in the x direction of B, there was nothing. The only component that existed was D's x component, which was negative 2.05. So imagine that we're here, and we're going to go out negative 2.05. There's nothing else. If B had an x component of, say, positive 1, I'd go over 1, and then I'd go to the left negative 2.05. But since there's only just that x component, this is the only thing going in this direction. So this x component is only going to be negative 2.05. Okay, so that tells us which direction we're going to go, negative 2.05. Now, on my y components, B's y component is 3. And what was D's y component? Negative 5.64. Okay. Now, here's the deal. There's a couple of ways you can visualize this. I don't care how you do it. I'm going to paint you both pictures. We went out here in this x direction, and you always do the x components first. You always do the x components first. Now, technically, from the end of that, we're going to go up 3 centimeters, okay? Because that's B's x component. So we would go up 3 centimeters. Then from the end of that, then we're going to go down negative 5.64. Okay? So we're here, we would go up 3, and then we go down negative 5.64. And that would leave us a difference of negative 2.64. Now, if you really wanted to draw it out, okay, if you really wanted to draw it out, that's what you would do. If you were big into measuring things, this is what you would do. Or you can just sit here and go, wow, I'll just take 3 and add it to negative 2.64 or negative 5.64 and get negative 2.64. Now, this is the most important part of this whole process, is this right here. those x and y components. So once you get those, here's what we've said. Instead of going up, down, and then drawing the resultant, we went over, up, and down. So here's where we ended up, and this is the most important thing to get. Let me change that part. We went out, we went up, we went down, and we have this. So here's what's important. This is now a right triangle. By having this as a right triangle, then we can use the Pythagorean theorem. Then we can use inverse tangent to find this angle, okay? So this is why we deconstruct the vectors into the x and y components, so that when we reconstruct them, we end up with the right triangle, and we can use the Pythagorean theorem and inverse tangent and all sorts of good stuff. But we can't use that if we've got this jacked up triangle here. But once we break them up into the x and y components, hey, then we're cool, okay? So, at this point, when you get to this step, okay, here's one of the things I absolutely beg you to do. When you get to this point, make a simple sketch. If you didn't sketch anything before then, hey, that's up to you, okay? I can't change that. This is the one where you really pays off to make a sketch. So just come out here and go, okay, hey, my x component is going to be negative 2.05. And then I'm going to come down here with that y component of negative 2.64, okay? And then I'm going to draw that resultant, okay? Yes?
So we don't have to draw the 3 centimeters going up?
No. No, because it's just going to basically cancel out and you're going to end up at negative 2.64. Because when you get past kind of the beginning stages, all you're going to do is you're going to go directly to this chart anyway. I was just showing you that so you have like a visual about what's actually going on. Okay? So, now, you all remember the Pythagorean theorem, right? A squared plus b squared equals c squared. Little bit of Egyptian history. Y'all remember like the magic one when you have 3, 4, 5, like a triangle, 3, 4, 5. Remember that? 3 squared plus 4 squared equals 5 squared. So that was kind of cool. And the Egyptians were the first ones really to figure that out. But where they ran into trouble was if you had a triangle that was 1 by 1, and then you had 1 squared plus 1 squared, and then it was like the square root of 2. And the Egyptians actually, the mathematicians tried to keep that as like a national secret because they didn't know how to handle the square root of 2, because they thought all numbers should be like whole numbers. And so it was like, oh, this is bad. We don't know how to handle the square root of 2. So they literally kept that, the mathematicians kept that as like a national secret in Egypt, like the square root of 2, because we didn't know how to handle it. And it was like, oh, this is bad. Okay, so Janine, let's try your calculator skills again. Okay, so take 2.64 squared and 2.05 squared, and then the square root of all of that.
$3.34.
Beautiful.
Nice.
First time too. 10 out of
Yeah.
10. Woo! Nice.
Thank you.
Nice. Thank you very much. Kind of that Elvis Presley thing. Thank you very much. All right. Now, is that a vector quantity if I just put 3.34 centimeters? Probably not. Why? What if that's the only thing I gave you? The magnitude. I've only given you the magnitude. I don't know which direction it's going. 3.34 centimeters. Okay, cool. So what? Up, down, left, right, 120 degrees, negative, I don't know. So that doesn't tell me anything. Now, here's the most critical thing. Okay? Here's the most critical thing. Is describing this angle from here over to here. Okay? Now, this is why it's so handy to make a sketch. And you have to look at how these angles are defined. So here's the deal. So, if you just take the inverse tangent of opposite over adjacent, if I just take negative 2.64 and divide that by 2.05, okay? And we'll put in the negatives. So, and you know we don't have to put in the negatives because there's two negatives in there and cancel each other out anyway. Anyway, so this is what I would do, okay, because I'm old, okay? And I learned how to do this out of a book process. If I were you, I wouldn't even worry about any negative signs when I do inverse tangent. All I would do is find this angle. I would just punch in the 2.64 and the 2.05. I would just find the angle. Now, this was the time-consuming part when you were doing this process, because if you were trying to find the angle, here's the first thing that you'd have to do. You'd have to divide 2.64 by 2.05. So do that. So just give me the number. Take 2.64 and divide it by 2.05.
1.29.
1.29. Okay? So then I'd have to go through this chart and find the angle that had something close to 1.29. Okay? And then I'd find the angle, so you'd have to divide that out. And then you'd go to here and then you'd find the numeric value and the angle that corresponded with that. So you'd have to do the division first, and then you'd have to work backwards and find this angle. You're all going, and you survived this? And you kept studying it in spite of all this? Yes, I did. So, or you could just take the inverse tangent of 2.64 and divide it by 2.05, and what do you get, Janine?
52.2.
52.2 degrees. Okay? Now, here's where you have to be careful. Rachel, if you tell me that your resultant is 3.34 centimeters at 52.2 degrees, if I told you that, where would you think that resultant is? Is this the international sign for first quadrant? Or John Travolta and disco in the 70s and you're doing this action? Don't ever let disco come back. I beg of you, don't let disco come back. It's horrible. So, if you tell me it's 52.2 degrees, I think it's up here in this first quadrant. Is that where it is? No, where's it at? Third quadrant. So what are you going to have to do? Yeah, you're going to have to add 180 degrees to it to get this angle. So you'd add 180 to that, and you would get 232.2, I believe. Okay? So now, there you go. So here's the process. You deconstructed the vectors, you find your x and y components. Draw this chart, okay? I beg of you, draw that chart. Now here's what I promise you. I give you my solemn word. I am never going to say, hey kids, draw this chart and then add it all up. And then on Monday, I'm going to come in and say, no, there's a shortcut way to do it. You don't have to draw the charts. Okay, that was just smoke and mirrors just to fill up time. Okay? I will always show you the fastest, most efficient way that will cause you to make the least mistakes. I will always show you that the first time. Okay? I'm never going to make you do this whole long process and then go, oh, you can just do it in one step. Okay? Because as a student, that would always just drive me crazy. Like, why didn't you show me that the first time? Okay? I will always show you the best method that I have found right from the beginning. So, set up these charts. Now, here's my other solemn vow. Is if you don't set up these charts and your answer is wrong, I am not going to waste a single breath of the ones that I have left on this earth trying to sort through random numbers to try and figure out what you have done. If I cannot clearly see a chart that says, oh, here's my x component, here's my y components, boom, here we go. If your answer is wrong, and I can't track that very, very easily, I'm done. Okay? I'm just telling you now. Love y'all to death, but I am not going to waste my time doing that. Okay? So, when you get down to like number 11, here's what I would recommend. You can make a sketch, because you got vector A, B, C. Okay, so you don't have to, there's A, there's B, C, boom. There's going to be your result. So the advantage of that sketch is that I know I'm going to have a positive x component of A, and I'm going to have a negative x component of C. I'm going to have a positive y component of B and a positive y component of C. So I'm going to have a positive x and a negative x. I'm going to have two positive y's. Set up your chart. Go, here's my chart. You got, I have no idea what I just drew. Oh. X, Y, A, B, C, and the sum. So you're going to fill in your x components here, get this sum, fill in the y components here, get this sum, then make that new sketch, and always draw your x component first, and then do your y component. So, I'm done. So, what I want on Monday is you're going to do this one, ABC, BCD, and then down here, because you on these, you already have these values, okay? You've already deconstructed them. You're just going to use the values from the front on this. Again, make a chart. If you want to write big, then do this on another sheet of paper. If you think you can fit this in neatly here, you can do it right here. I don't care. But then you've got two other ones that you're starting from scratch. A 5 Newton at 60 and a 10 Newtons at 80, and then a 5 Newton and a 100 Newton. So I am done. So you have the rest of the time to work on that. And so here's what's going to happen next week. Okay. So we're going to start forces in detail on Monday. So on Monday, it's going to be, Monday is a good news, bad news day. I've got a lecture the whole day, but I'll do some cool demos. And then you won't have any homework Monday night. Then on Tuesday, we're going to finish up that discussion and start a lab, which you guys will be doing. And then I got to figure out how that, because that lab actually takes like 2 days, which kind of sucks because that second day would be Wednesday. So that's what I got to figure out how the middle of the week is going to play out, okay? Because that's going to get a little bit weird because we've got Wednesday right on that day that I really want to have like that second day follow-up lab, so we'll figure it out. But anyway, so Monday we'll start forces. We'll start that lab on Tuesday, and then we'll figure out Wednesday and then the rest of it. But this forces unit is going to take about 2.5 weeks to get through because we've got a whole bunch of labs to do. So that's the good thing. So if you like labs, you're going to really like this unit because we got a whole bunch of them coming up. So, all right, that is the story. Give me that assignment on Monday, and that's it. So that's it. You have the rest of the time. Yes?
The vector assignments due Monday, right?
Yeah, this one. Yeah. Yeah. It is due Monday. All right, we're done. Josh, have a good weekend.
Wait, where was we supposed to get this
Where's what?
assignment? Where was I supposed to get this assignment that I just?
Okay. So there's the lecture notes.
Oh,
And then, nope, that's not it. You're supposed to pick it up on Tuesday after the test. Who's that? Anybody else need the assignment? Good? Okay.
Everyone else has it together.